Welcome back, fisheries scientists, physical oceanographers, meteorologists, depending on which chapter we're in. My fun fact of the day I just learned, Jamin says he's like 1,000 times better at Fortnite than Cash. So I don't know if that's true or not. What do you think? Okay, cool. I'm terrible, just for what it's worth. I don't play it because I don't like spending all my time waiting to be revived. Like, nope, not my thing. All right. Here we go. We are starting chapter 5 today. And a lot of this stuff I think you've probably seen, but if you're juniors and seniors, it's been 4 or 5 years since you've taken Earth and Space Science in middle school. Cool. So, the one neat thing about this is when you guys say, no, I don't remember learning this ever, so forth and so on, I get to go home tonight and tell Mrs. Holloway that your students don't remember any of it. So, she'll probably comment in the coming days. Let's check it out. Chapter 5 as a whole is going to look at 2 different things. Obviously, in a fishery science class, we're talking about the oceans. Okay, makes sense. Now, the oceans interact with the atmosphere above the oceans in a lot of different ways. And what they wind up doing is they circulate in a variety of different ways, energy, nutrients, all those things around the planet. So, we are not in a strict Earth and space science class. But if we didn't know anything about how these two are related or how each of them impact one another, now's your chance to get it knocked out. So right to begin with, we're going to start with the atmosphere. And in 5.1, we're just looking at atmospheric circulation. Okay. As we look at the atmosphere, there are generating forces for waves. And I know we're going right back to the ocean. Do some waves get generated because of storms? And what makes storms? Hot and cold. Typically, that's a pretty easy way to simplify it. I like that idea. How would hot and cold do that?
They're change their difference in energy.
They're different what?
Their difference in energy.
So the difference in energy that they carry? Absolutely. Now, there are a lot of ideas that we're going to see in here. And if I'm going way too fast, just let me know. Cool. Have you guys talked about the atmosphere in detail before? Where does the atmosphere start? Like right there, right? Like a meter that way. Down like literally a meter below me here. So as we're looking at this, there's a few different ways that this winds up getting formed. Our first main section, and it feels so redundant and I hate it. Can we just agree that atmos is going to be atmosphere? Cool. Atmosphere or atmospheric circulation. Now, if we're on Earth, and I'm like, I think we are, we're pretty sure we are, or I'm having like the most defined dream ever, and I'm going to have another day at school here in a minute. However, we're on the planet, and there's distinct area on the planet and off the planet, right? If I go to space, what do I need? I'm going to need oxygen. Why? So I heard 2 answers. I heard there's none in space and there's less. Which one do you think it is? It's less. Now, here's a weird idea. Whenever you look at the Earth and things like that, we like to think in really defined boundaries. We do it as people, right? Like you're on the island or you're off the island. You're in the U.S. or you're not. It's a pretty natural thing that we just do. Turns out there's not really a fine distinction between you're in Earth's atmosphere and you're not anymore. Because space, pretty much nowhere in the universe are you going to find a true vacuum, which is just the absence of anything. There's gases out there. We know that there's big clouds of gas that aren't in our atmosphere. They're called nebula. You can look at them. You can see them up in the stars. Stars get made, black holes born and die, and all of that stuff happens in big clouds of gas that float out in space. So clearly there's a way for gas to be out there. As we look at our atmosphere, though, we have within what we would consider the true atmosphere of Earth. Really simple to define. There are 4 layers to our atmosphere, and of these 4 layers, we need 3 boundaries. 4 layers and 3 boundaries. That's what makes up our entire atmosphere. Now, obviously, there's a lot of gases within our atmosphere, right? What's the most common gas that you're breathing in right now? It's not oxygen, although that's a good thought. It's not carbon. It's nitrogen. Like 70% of it's nitrogen, 20% of it's oxygen, the other 10% is just a bunch of random stuff. So as we look at this, I suggest that rather than like true defining stuff, we can just draw a similar picture that's in your text, and we'll just talk about them as we go through, rather than like super detailed notes. Okay, now when I do it, it might annoy you, but just open to ideas. If we're looking at these 4 distinct layers, can we draw the Earth like this, like that's a portion of the Earth? Now, it's the bottom of the Earth, right? But are we okay with that? Okay, as we move down away from the Earth, so down in this picture, up from our perspective, or anybody's perspective if they're on the planet, you're going to pass through these layers. So the very first layer that you're going to encounter, and I'm just going to do it like this, we go from about 0 to 20 kilometers. Now, 20 kilometers isn't a pretty, like, we don't think in kilometers most of the time. Roughly how high in miles? Anybody have an idea? Pretty close to 10, 11. Like, we're not super high up there, right? Okay, higher than your commercial jets will fly, but certainly not higher than, like, military aircraft will fly. They can go to, like, 100,000 feet. So as we're looking at this, the very first layer that we hit is called the troposphere. Now, this, I would argue, especially when we're talking about weather and how energy and stuff moves around our planet, this is probably the most important one that we have to deal with. Because this is the closest to the planet, which means whatever conditions it is experiencing are the conditions that you're currently experiencing. Now, there are other, obviously, that we care about. But as we're looking at the troposphere, all I'm going to do is we'll just have these not to scale on the side, and we'll just make a couple comments about each. Okay, for this, right now, what happens as you climb an elevation? Like, let's say I'm here, and all of a sudden we are transported to the top of Pyramid, for example, so back there. So the pressure might change a little bit, for sure. But what happened to the temperature? It would change. Would it get colder or hotter? Colder. So we all agree that temperatures decrease as you go up. Okay. So kind of, but we'll get there. So in the troposphere, temp decrease as altitude increases. Everybody okay with that? An inverse relationship, typically. Now, I saw something the other day that it was on teacher TikTok or whatever that you want to look at. But somebody was just like blasting a kid for, they said this kid asked a dumb question, and I think that that's awful. There's very few questions that I would consider as dumb questions. As you climb up in height, what do you get closer to? You definitely get closer to the sun. And closer to a big, nuclear reactor in the sky, what should happen? Why doesn't it? Like, so I saw a teacher just blasting that question. I think that's a valid question. If we go up in the air, we're closer to the sun. Why is it colder? Talk it out. I want to hear ideas. Like 30 seconds or so. So heat rises, which means it should be warmer up here? Like, all those are good ideas. Like, they're on the right track. Now, there's a lot of different answers, and this isn't specifically addressed, but I think it's worth just thinking about since, we care a lot about the temperature in general. Where does most of the sunlight actually land on our planet? Now, there's really only 2 options. The surface of our planet, take away all the people and all of that. You're either going to land on the ocean or where? On land, right? Now, if you go out in a hot day, like if you're on a fancy beach and the sun set 20 minutes ago and you go walk on the sand, is it still warm?
Yeah.
Depends on where your beach is, right? The ground will hold a lot of that energy. So will water, in fact. That energy then radiates up, and as it gets rising, and that's part of what Caden had mentioned a second ago, there's more energy close to the ground because it's reflecting and energizing or bouncing out of the ground, right? Not bouncing necessarily, but you heat up a rock and you stand above it, it's going to be warm right there compared to if you go way up above it. Okay, so one idea there, I'm good with it. Now, as we look at this, there's a weird little range thing that keeps happening, and again, we don't have physical distinct layers to this other than something changes in between here. So, we go up and we get down to about negative 60 degrees Celsius at what we're going to call our division. Now, the troposphere is between 0 and 20 kilometers. There is, however, a kind of gray area, so we'll just go ahead and say, check it out, there's a gray area, where it separates the troposphere from the next level up. This is called the tropopause. It's where we see a distinct differentiation between the troposphere, which this begins at about 12 kilometers up to 20, so that all counts, but we start transitioning. We have this area, and it's here where we start to get these really, really cold temperatures. Okay, nothing too crazy. Most of our weather happens there. If you need this, this is the tropopause, and we're going to have that word with pause show up over and over. Okay. Once we go beyond this, we start to get a little bit bigger. So we're going to take our next trip from 20 kilometers, and we're going to keep going up and up and up to about 50. I'm going to say 0 to 20 to 50 kilometers. We'll just write it consistently. Okay. We're now a little bit higher up, right? 20 to 50 kilometers, that's pretty high up there. So as we're looking at this, we enter what is known as, and I'll just switch colors, the stratosphere. That's going to annoy me, but I'm just going to commit. Okay, the stratosphere is higher up, and there's a lot of really important stuff for you, for me, for everybody that exists in this level. If you read through it, you probably hit a really special version of oxygen. Maybe not. Okay, we see something different happen here. We see temperatures falling as we move through the troposphere and we get higher and higher up, or further away from the Earth if we want to think about it that way. All of a sudden, when we get to the stratosphere, though, we see something wonky happen. In the stratosphere, we start to see increased temperatures. So we were falling temperature here the whole way as we went up, but temps start to increase again. Now this whole idea gets even harder to think about just as we're seeing it. This was a surprise. Right now, how many of you guys wear sunscreen? If you go to California, you're going to go walk around. How many of you put on sunscreen? I do. Who should? Literally every single person in here should. You should use safe sunscreens that aren't destroying reefs and oceans and such, but you should wear them. Why? Why do I wear sunscreen? Obviously I'm white, but more than that. Protect my skin from what? UV. What's UV stand for? Ultraviolet. Now, UV light, it's kind of a double-edged sword. It's terrible for humans, but necessary at the same time. We have proteins in our body that take UV light to produce vitamin D. You need sunlight as a human being. If you don't get enough sunlight, you have a vitamin D deficiency, and realistically, most of us probably have a bit of a vitamin D deficiency here. Anyone here take vitamin D supplements? Cool. If you've had if you ever noticed you feel kind of sadder in the wintertime, it's called seasonal affective disorder. It's a real thing. Vitamin D deficiency is a big cause of that. Obviously, there could be other things that are bigger than that, but temps begin to increase in the stratosphere, and I know that we're talking about vitamin D. I would get way more sunburned here. Now, there's something that exists in our atmosphere that during the 90s there was a big talk about how scary the big hole in it was, because if we had something missing, UV light gets in and more people get skin cancer. What protects us? Several things, but what's the one that we're talking about?
Ozone.
The ozone layer. Okay, when you breathe in oxygen, do you guys know the chemical symbol for oxygen? H is hydrogen, He is helium, so it's just O. Now, oxygen, like O for oxygen, O2 because it shows up as a diatomic. That's what it's called. Di meaning two, atomic meaning atoms. Two atoms, O2 is what we breathe. Now, oxygen is not the same everywhere. We have O2 that we breathe and it's safe, we can deal with it. When we get up here, these temperature increases are due to a special type of oxygen. Now, you're going to write ozone, and that was a weird emphasis. Ozone is a triatomic, O3. Now, what ozone does in this is it absorbs a ton of this UV light. Not absorbed, but absorbs UV light. Now, the discovery of UV light's pretty cool. Not really our focus, but you can't see it. I can't see UV light. You guys can't see the true UV light because it's outside of the visible spectrum. What's the highest energy light that we have? Purple, or give me a better word for it. Violet. If you go above violet, you get to ultraviolet, and we can't see it anymore. It was discovered by somebody shining light through a crystal and seeing a rainbow, and putting a bunch of little amounts of water and seeing temperatures change depending on what color lights it up. And then he had one extra way out here past the violet that got hotter than all the others. It's because of UV light is what was striking that, and we just discovered at that point in time. Now, ozone absorbs and reacts really well with these UV light, which means all that energy that comes in the form of ultraviolet light waves gets stuck in the ozone in the stratosphere. This is responsible for the increase in the temperature. All of that extra ozone. Now, ozone does get used down here on, like, down south. By down south, I mean low elevations. Do you guys think of anything that ozone is used for? I have a feeling there's probably applications with welding. I would almost put money on it in some fashion. Other places it gets used is to treat scent stuff. So if you have some like really smelly production that you have, you can pump ozone around it to help deal with that smell. It'll also poison people, so you don't ever want to breathe in like true ozone. But it does exist and it has applications. Now, we keep going through this and we're just going to use our powers of deduction. We keep rolling up to 50 kilometers. And then there's like another little gray area that we're going to deal with. Okay, powers of deduction. So we're at like 50 to 55 kilometers right now. We go through the troposphere until we hit the tropopause. What do you think happens at the end of the stratosphere? The stratopause. Okay, absolutely. Exact same word, this distinguishing area between the stratosphere and our next. So we get our lovely stratopause. Okay, now our stratopause happens. We see these regions getting bigger and bigger and bigger. There's really only two more that we care about, at least in depth. We're going to jump one more trip. Let's go like 55 to 90 kilometers. Now, we don't have a ton to say about this one, so I'll try to stay consistent, but we can just write it on here. We go troposphere right away. Then into the stratosphere with all of our ozone. Then we wind up in our mesosphere. Mesosphere. Can you say that louder? Stratopause. Just like we saw tropopause, same language. Which, if we skipped ahead, we'll write it here in a minute. What do you think is going to be distinguishing between the mesosphere and the next one? The mesopause. It's going to happen. Now, these ones, only a couple of little brief comments. And we'll use that one. I'll make it a little bit more bold. Right off the bat, all of our ozone, or our O3, mostly gone. Because there's no more ozone there to take up and absorb all this UV energy, what do you think happens with temperatures again? They start to drop again. And we see that same, no more O3, temperatures start to fall. So temp, fall. Okay. We don't have anything else to say about that. I'm going to make this section, I lied. I will just do the same thing. We'll make this nice and gray. Okay, until we get to the mesopause, which is what somebody said a second. Ugh. The mesopause. I hate it. So much I hate it. Cool. Now, are we in space yet? Not formally. Could you breathe? Not a chance. I mean, you could breathe in, but the air is so thin because of pressures that we've been talking about that you're not going to get enough oxygen to live. You go up this high, one, you're going to freeze to death pretty quickly. Two, you might suffocate first, so maybe you won't freeze to death. Just depends on the situation. Okay, we go past the mesosphere and our last true region that we're going to talk about. The very last one that we get to, and I'm going to call this one red for now. We get all the way up to our thermosphere. Now, for this, we are super high up at this point. We were at 90 to 95 for our mesopause. We're going to jump back in at 95 kilometers high, all the way up to, and this is rough, but we're going to say 500 kilometers. Roughly. Not exact, because there's no true defining region. But we're 500 kilometers high right now, which that's a ways up there. Okay, in this region, not a ton of stuff to say about this one either. All of our O3 is here. It's a little bit heavier, so it stops in our mesosphere. There's a little bit more O2, diatomic oxygen, back here. Not enough for you to live. but we do see a little bit of oxygen starts absorbing, so we see temperatures rise again. We're rising, falling the whole way through, and it's strange, but we'll just say O2 in small quantities. Temp increase. Now I am going to be honest, I have no idea exactly what the temperatures that we're talking about are here. Once we get to negative 60, we're super cold. I'm fairly sure that in the stratosphere, even with all the ozone, you're not going to get like life-sustaining temperature. It's just not going to happen. We're too high up. Okay, in this, we're pretty much at the edge of space at this point. You're not going to find low Earth orbit with satellites and things happening here, but you're getting real close. Last one that we're going to write today with this. I'll tell you the next one's going to be called the exosphere. Exo as in out of or exterior. What do you think we're going to call this boundary between the thermosphere and the exosphere? It's the thermopause. Yeah, like there's no surprise here. Thermopause. Now, the very last region that we deal with, I don't have anything to say other than I'm going to mention it. And this is where just the lack of clarity, it happens. I'm just going to say that this is roughly 700 kilometers and plus. Yo. Yep, there's a sign-out sheet there, okay? Once we're here, we're in the exosphere. And at this point, you could say comfortably that I'm in space. You would be in space for all intent and purpose at this point in time. All it takes is 500 kilometers up, and you're pretty much there. Now, as we go through this, we care of these layers, which one is most impactful on you as a human being on this planet? I'm not even going to show the exosphere. I don't care about it. What do we care about most, do you think? So stratosphere is super important because of blocks of UV, for sure. Which one do we spend all of our time in? Literally all of our time is in the troposphere, right? We hope that the ozone is there. Last time the world made it seemingly like a concentrated effort that every country just says, let's agree, was to stop these things called chlorofluorocarbons that came in like cans of spray. And they were used in industrial levels, but it was eating a hole in the ozone layer. And the world, everybody in the world said, I don't care what your beliefs are, let's just agree to stop using these. And everybody's like, yeah, let's do it. And it was cool. Okay, we care most about the troposphere, and only because we spend 100% of our lives, unless you're an astronaut or a pilot, in this. So, as we go through here, one of the big things that our planet does and does really well is it moves energy around. So, our next big topic, and whether we start it right this second or not, we'll decide. But we need to talk about how the atmosphere gets heated. Heating the atmosphere. All right, so little hands-on stuff. I'll get a couple more of these. Can you get them? Yeah, 100%.
Oh, man.
All right.
We're not sleeping in class, are we?
So, well, hold on here. Let's not hit the things. Hold on to these because we're going to use them for a second. Huggins, you got one. I need one for you guys. Okay. I'm going to blow another one up real quick. Okay. First thing that I want you guys to do, and I'm going to blow one up for your guys' groups. You have one. You have a planet in front of you. Right off the bat, you guys have all taken geometry, I think, yeah? How many degrees in a triangle? 3. I'm pretty sure it's 180 as well. 180 degrees in a triangle. There's one group that's going to ruin this, and I'm just going to say don't. Can you draw me a triangle that has more than that? Try it. Draw me a triangle that has 270 degrees. You can do it. Draw me a triangle with 270 degrees. Sure. On paper's fine. Doesn't have to be on paper. Can you do it? Okay, so not really our of paper can be challenging, right? Like every triangle that you've ever seen has how many degrees? 180, okay. All the time. That's like what it means to be a triangle. In Euclidean space is what it's called. Euclid being the guy that like discovered geometry and wrote the book that was used for 2,000 years. However, I think it's your glove that ruins it. On this guy, we're on a sphere, right? If I start at the South Pole here, can I go in a straight line down to the equator? Like, you say no, but on a sphere, would a straight line just be this? Like, I think so, and I agree that it's a curve when you're looking at it, but like if I show you this line right here, is that a straight line? It's on a curved surface, but it's a straight line, right? Okay, if I go down from the North Pole to the equator, can I turn 90 degrees? So here's me doing that. Down, 90 degrees, over, yeah? If I go a quarter of the way around the globe and now I turn 90 degrees again, can I come up here, back to the top? How many sides does that figure I just drew have? 3, and it's a triangle then, right? 3 sides, it's just a 3-dimensional triangle at this point. And 90 and 90 and 90, we can do it. We can make like ridiculously big triangles. Geometry that you all deal with in the math is fine and dandy. It's good to develop those skills, but they're not really real skills yet, depending on how you want to apply them. Okay, so on this, first thing I want you to do is, with your group, I know that the Earth spins. I want you to determine which way does the Earth spin. I would hold north to the north. Think about what you've seen in your life. I want you to be able to rotate this globe one way or the other, and to convince me that you're correct. Which way does the globe spin is the question at hand. Cool. Think about it. If you guys have ever watched the sunrise, you have enough to solve this question. When you talk about which way does our planet spin, it gets weird to really go into it because you have to make sure we all agree that we're looking from the same place. If I looked from the south, I would see it spinning clockwise. So things get weird, right? Okay. Beyond that, do me another favor. I want you guys to estimate. We all know that the sun doesn't sit perfectly flat on the plane with our sun, right? The planet is tilted. I want you to roughly, just on a globe, take it so that north is straight up towards the ceiling, and then tilt it to how far you think our planet actually sits. So I'm not looking at you just, I'm just looking at you. You're probably pretty close. Too much. Too much. I bet you're pretty close. Where do you think it is? What? No, so if I'm the sun, how sun's tilted, or the earth is tilted. Okay, like way more than I just looking at it. Now, more than that. As we look at it, the sun winds up tilting at like 24 degrees-ish. Pretty close. So just to highlight that, this much. It's pretty stinking tilted. Like more than you might think. As we look at it, that has a huge impact on the heat that our planet receives. When we go through seasons, what's the cause of the seasons? The what? So the weather is determined by the season we're in. But what causes the difference between summer and winter and all that? Something with the tilt. Now, oftentimes when kids learn this, not that you guys are kids, does our planet orbit in a perfect circle? No. Now, the way that this is presented incorrectly and not intentionally or not for a mean reason, but our planets actually orbit in ellipses. So it's like an oval that goes around. Commonly mistaught in our country is that we're closer to the planet here, closer to the star, sorry, so it should be summertime, and we're further from the star, so it should be winter. That may be how you were presented this idea, and it's a nice thought, but it's not true. Because the entire Earth would be closer here, which means you would get summer in the northern hemisphere and the southern hemisphere simultaneously. Does that happen? It's winter here. If we go to Australia, what are they celebrating? Summer. It's summertime for them. Now, the reason for that is directly related to that obnoxious tilt of our planet. So, last little thing that we're going to knock out today is just a small picture. I'm going to go ahead and draw our planet here. So here's our planet. And if we have the axis of rotation, I'm not going to measure it, but it's about like this, like more than you would think. So that's about where we spin, which means our equator would run about there. Okay. In this situation with where we're tilted, if I put the sun right in the middle, and here's a big sun, it's going to blast out some light our way. Here's the other side of the planet, a later time in the year. One of these pictures is summer for us, one of them is winter, and I hope, and I think it's probably pretty clear which one's which. Which one of these, and they would go the other way, so it'd be like this now. Which one of those is summer for us? The one on, wait, did I just do it the same way? I just did it the same way. No, I'm goofed up. I did it the same way. Did you guys notice that? Our planet's tilt doesn't change. Our location does. There we go. Okay. Which one of those is now summer for us? So if we look at the left, who's closer to the sun, the southern or northern hemisphere?
Yeah.
Down here we get summer, right? Because look at how much closer we are. Now maybe it's not so much the closeness that really matters, because there's not a huge difference. We're going to dig into this, and I'm going to have a better picture. We're going to go to the hatchery tomorrow. I thought we'd go today, but I was psyched about this. I think we're through the most boring part of it. Yeah, that's always the goal. Cool. When you're playing with the globes, heads up, I'm not sure, but I'm afraid that if you hit one of these hard enough, you're going to make the school flood. So don't do that. 2, you can just leave them on your desk and I'll come grab them. Later Raiders, poster decorating in 15 minutes if you're Pepper.